of you. I hope I am perfectly audible and visible to each and everyone present over here. Okay, anyway, warm welcome all of you to the Infinity Learn JEE YouTube channel. This is me Surya, your chemistry faculty from Infinity Learn. Today we are going to our next part of the same chapter, that is chemical bonding and molecular structure. Before that, I have to inform one more thing, that's about their ionic character, right? Whenever we are discussing about the covalent bonds and ionic bond, there will be some character. Not a complete molecule is 100% ionic or covalent. So I have earlier informed that about the Fajan's rule, right? So before starting our new session, I will discuss about the Fajan's rule first. Okay, what do you mean by a Fajan's rule? I have already discussed that there will be a covalent compound. It has not 100% some ionic character, right? Similarly, in the case of ionic compound also, it will experience some covalent character. So, in the case of any covalent compound, we can say that there will be some ionic character, right? Hi Anish, good evening. Okay, in the case of an ionic compound, there will be two types of ions, right? Cation as well as, cation as well as anion, right? If I am taking a cation having positive charge, right? This is our cation. This will be our anion, right? Cation will be small in size and anion will be larger in size. So, in the case of cation, this positive charge has an ability to attract the electron cloud from the anion, right? The electron cloud from the anion. So, what will happen? If the positive charge on the cation attracts the electron cloud on the negative charge or the anion, the shape or the complete structure of the anion will changes, right? There will be a distortion will happen, right? So we can say that this happens because there is a change in structure or the shape of the negative charge. That process is known as the polarization, right? That process is known as polarization. Clear? Yes, Aditya, VSEPR theory is for shape prediction. I am discussing about the character, Fajan's rule only, right? Before entering into the VSEPR theory, I am just completing the Fajan's rule. Fine? Okay, this is the process of polarization, which means that cation has the ability to distort the structure or the shape of the negative charge anion. Similarly, this ability of the anion to change their shape is known as the polarizability. Then the cation has the polarizing power, right? So, in the case of an ionic bond, covalent character is experienced. This is explained by the covalent character of ionic bond is explained by Fajan's rule. Clear? The basics about the Fajan's rule or the polarization. Is the thing clear? Now let us see what you mean by the Fajan's rule or what are the things happening on the Fajan's rule. So, I have already discussed that there will be a covalent character for the ionic bond, right? So, covalent character of the ionic bond increases as the size of the cation decreases or size of the anion increases and the high charge on cation and anion. I will be explaining with the examples, no need to worry. So, if we am taking this example, right? These are the chlorides of group 1 compounds, right? Lithium, sodium, potassium, rubidium, cesium. While moving from lithium, sodium, potassium, rubidium to cesium, what will happen to the size? Size is increasing, right? The size of cation is increasing here, which means that as the size of cation increases, the covalent character of the ionic bond decreases. There is an inversely proportional relationship, right? So, if you are asking for the order of ionic bond nature, it will be the direct proportion, right? As the size of cation increases from lithium plus, Na plus, K, potassium, rubidium, cesium, size increases, which means their ionic character increases or covalent character decreases. Clear? How the size of cation is affecting the covalent character of ionic bond? Now the second factor is the size of the anion. If you are taking the large anion, for example, here, right, this is the same compound of calcium. I am taking fluorine, chlorine, bromine and iodine. What will happen to the size of fluorine, chlorine, bromine and iodine while moving from top to bottom in a group? Increases, right? As the size of the anion increases, the covalent character of ionic bond also increases, right? So we can say that the covalent character increasing the order of CaF2, CaCl2, CaBr2 and CaI2. Then what about the ionic bond order? It will be the just reverse, right? Clear? The next parameter is about the high charge of cation or anion. If you are taking this example here, right? NaCl, MgCl2, AlCl3 and SiCl4. What will be the charge here in the case of cation? These are the chlorides of different elements, right? This is sodium. What will be the charge here? +1, right? Na plus Cl. Then here MgCl2, which means it is +2. Then here it is AlCl3, Al plus 3. SiCl4 means it is Si plus 4, right? Which means that the charge on the cation increases. Similarly, if the charge of the anion also increases, there will be the increase in covalent character, right? So this will be the increasing order of covalent character of ionic bond. Clear? Aditya, is that clear now? Okay, so far we discussed about the ionic nature as well as covalent nature. Now I am directly moved to the next topic, that is the VSEPR theory. This is a very important theory while discussing about the chemical bonding. Okay, what do you mean by VSEPR theory? There is something hiding here, right? VSEPR. Any idea? Yes, VSEPR stands for Valence Shell Electron Pair Repulsion Theory. The name itself suggests that the basics of the theory, right? Valence Shell Electron Pair Repulsion Theory. Do you have any idea about that? What does it mean? Okay. According to the VSEPR theory, we can predict the shape of the molecules, right? We have already discussed about the causal-Lewis approach. The main limitation of that law was it is failed to explain the shape of the molecules, right? So the second theory came that is the VSEPR theory. According to this theory, it is discussing about the procedure to predict the shape of the molecules, right? To predict the shape of the different molecules. Then how these shapes are coming? Depending upon the valence shell electron pair repulsion, which means that the electron pairs which present on the valence shell have a repulsion, right? These electrons have the same negative charge, so it will repel each other. Because of that repulsion, in order to minimize that repulsion, they will be moved into the more distance, right? So that will be the basics of this valence shell electron pair repulsion theory. So as you can see here, this theory is based on the repulsive interactions of the electron pairs in the valence shell of the atoms. And it was proposed by Sidgwick and Powell. Later it was modified by or developed by Nyholm and Gillespie. Clear? Now let us see what are the main postulates of the VSEPR theory. Yes, fine. What are the main postulates of the VSEPR theory? There are many more postulates which is shown in your NCERT. These are the brief notes for this VSEPR theory. You can note it down. The first one, the definition of the VSEPR theory itself is that the shape of the molecule is determined by the repulsion between electron pairs. Repulsion between electron pairs present in the valence shell of the central atom. Valence shell of the central atom. Right? Okay. Now I have a question for you. Maybe you have an idea about the electron pairs, right? There are two types of electron pairs in a compound. What are they? One should be bond pair, right, which is involved in the chemical bonding. Then another one is the lone pair, which does not involve the chemical bonding, right? So that electron pairs are known as the lone pairs. So in the case of molecules, there will be two types of electron pairs. One is bond pair and another one is lone pair. According to this bond pair, lone pair, there will be some repulsion. That is why the shape or geometry of the molecule changes. Then I have already mentioned that there will be repulsion, right? Because both of them are the electron pairs, there will be some repulsion. So it will move apart. So there is a thing to be noted that this is the order of lone pair bond pair repulsion, which means that the lone pair repulsion is more than that of the bond pair than bond pair repulsion. Clear? This point is very, very important. According to this lone pair bond pair repulsion, we will explain the shapes or geometry of different molecules. Then the third postulate of the VSEPR theory is that as the repulsion is always increases with the increase in number of bonds. So if we are considering the single bond, double bond, triple bond, as we are moving from single to double to triple bond, right? Number of bonds increases or bond order increases, right? What will happen to the repulsion? Repulsion will be more, right? Repulsion will be more. Then, in order to simplify this law or theory, if we are considering any of the molecule, right? If any of the molecule contain multiple bonds, which means double or triple bond, we will be consider this bond as a single electron pair or single bond, right? Clear? For example, if I am taking any of the molecule here, right? This will be our molecule. So in total, it contains 3 bonds, right? 3 bond pairs. But according to VSEPR theory, we will consider this double bond also a single bond, right? We can call it as single bond or single super pair in case of double or triple bond. Clear? Now, we will be discussing about the shape of the molecule. If there is no any lone pairs on the central atom, there will be the same shape or geometry as shown by the hybridization, right? I hope everyone have a little bit idea about the hybridization. Or not, we will discussing in the next class also about the detailed explanation of the hybridization. As you can see here in this table, here, if the electron pairs contain, if it is 2, okay, if the molecule contains only 2 bond pairs, it will have the shape of linear, right? Which will be in a straight line having the bond angle of 180 degree. Then, if the number of bond pairs is 3, it will have a shape of triangular planar with 120 degree. Then for so on, right? You can see here, we will be discussing detail. If there is no any lone pair, if bond pair was there only, then we can predict the shape of the molecule as expected by these geometry or shape, right? So, the next case arises that if they have lone pairs on the central atom, what will happen? If lone pair is there, no, there will be more repulsion, right? There will be repulsion between lone pair and lone pair. So, in order to minimize this repulsion, it will change their shape. That is mentioned here. If the molecule contains both lone pair and bond pair, then its geometry changes so that it acquires minimum repulsion. Clear? These are the main postulates of the VSEPR theory. Yes, fine. Now I have a question for you. Is there any difference between shape and geometry, or whether it is same? Shape and geometry. Any difference, or it is same? Fine. If we are discussing about the shape, it means that we will consider bond pair only, right? If we are considering the bond pair only, we will get the shape. If we are considering lone pair also, because of the repulsion, the shape changes, so they will call it as geometry. Clear? Now we will be discussing about the molecules with 0 lone pair on the central metal atom. There will be 5 types. The first type is AB2 type. AB2 type means there will be 2 bond pairs, right? 2 bond pairs and 0 lone pair. Two bond pair and 0 lone pair. The example is beryllium chloride. So, for example, if I am taking the same AB2 type, right? This will be the arrangement, which means in the central metal atom A, 2 B atoms are arranged in a straight line. So, what will be the angle here? In a straight line, Hag-Irwer 180 degree, right? In a straight line, 180 degree, there will be the maximum distance, which means that minimum repulsion of maximum distance. So it will arrange in a 180 degree manner. So we will call this shape as linear, right? Linear shape. Now, what about the second case? It is AB3 type, right? AB3 means this is our central metal atom. Then, other three atoms B are arranged in a manner. We can say that it is in a trigonal planar manner, right? A triangle planar manner with a bond angle of 120 degree. So we can say that trigonal planar will be the shape of this molecule of the AB3. Example is given here, it is BF3. Boron is a central metal atom having 3 bond pair, right? 3 bond pair and 0 lone pair. Clear? Now let me move to the third type of molecules, that is the AB4 type, right? What will be the bond pairs here? AB4, how much bond pair will be present? AB4 type. How much bond pair is present in AB4 type? Four, right? 4 bond pairs are present here, and again 0 lone pair. Then you can see here, this is our central metal atom A. Then I am arranging 4 B atoms here like this. In general, there will be a bond angle of 109 degree 28 minute. Then this shape is tetrahedral, right? Tetrahedral. Clear? The next one is the AB5 type, which means that 5 bond pair is present with 0 lone pair. Okay, this will be the shape of this particular molecule having 5 bond pair and 0 lone pair. Here, this angle will be 90 degree and this angle will be 120 degree. 2 bond angles are present over here. Example is PCl5. Clear? Then shape is around trigonal bipyramidal. As you can see here, this will be a trigonal shape having 2 pyramids. Clear? The last type is the AB6 type, in which 6 bond pairs are present with 0 lone pairs. So I am taking here 6 bond pairs. This will be the shape of AB6 molecule having the bond angle of 90 degree, right? Okay, my drawing is not perfect. As you can see here, it will be 90 degree. Then, example is SF6 having the geometry of, not geometry, the shape of octahedral, right? Clear? So far we discussed about the molecules, the shape of the molecules with 0 lone pair. Now the next condition is that if there is any lone pair of central metal atom, what will happen to the shape, right? Geometry arises there, right? If you are considering lone pair, also geometry arises. And this is a brief idea about the molecules with zero lone pair on the central atom. It is already present in your NCERT textbook. Girwar, I am passed out from NIT Calicut. Okay, these are the summary about the molecules with zero lone pair on the central atom. Now let me move to the molecules with lone pair on the central atom. You have to be memorize all the table. Now the first condition is AB2E type. Okay, here this number represents the number of bond pairs and E stands for the number of lone pair. So you can say that it contains 2 bond pairs, right? 2 bond pairs plus 1 lone pair. 2 bond pairs plus 1 lone pair. So what will be the structure here? This is the geometry, right? These are the 2 bond pairs and this will be the lone pair. So we can say that it must have a geometry. It must have a geometry of trigonal planar, right? It must have the geometry of trigonal planar. So, as I mentioned that if we are considering the bond pairs only, it will have the shape, right? So, if I am taking these bond pairs away, I am just hiding this lone pair, what will happen to the shape? What will be the shape here? If I am considering these bond pairs only, BB, what will be the shape? Bend shape, right? It is like a bend shape. So we can call it as a bend shape. So according to this, if we are containing 2 bond pairs and 1 lone pair, actually its geometry was trigonal planar, but because of their repulsion, the shape is having to be bent. For example, SO2 molecule, right? Example is very important. One is SO2 molecule. One is SO2 molecule and other one is ozone molecule. Clear? Okay, the next type is AB3E type. Okay, AB3E type, which means it contains 3 bond pairs and 1 lone pair, right? 3 bond pairs and 1 lone pair. Then this will have a geometry of tetrahedral, right? This will be the lone pair, this will be the bond pair. We can have the geometry, geometry of tetrahedral. But as we are considering these bond pairs only, it will have the shape of trigonal bipyramidal, right? It has a shape of trigonal bipyramidal. So we can say that in the case of 3 bond pairs and 1 lone pair, it must have a shape of trigonal pyramidal. For example, if you are considering the ammonia molecule, right? For example, about ammonia molecule. The next case it is AB2E2, right? AB2E2, which means that 2 bond pairs and 2 lone pairs, right? It contains 2 bond pairs and 2 lone pairs. So again, whenever we are considering about the water molecule or any other molecule, we will experience that, or we will feel that it will be in the tetrahedral structure, but it must contain 2 lone pairs, right? Because of the presence of that lone pairs, it will show like a bend type structure, right? This will be the shape of water molecule. These are the 2 lone pairs. If we are considering, if I am hiding the lone pairs here, this will be the 2 bond pairs, right? So again, it will be in a bent shape. So the shape of this particular molecule will be bent. Clear? The next type it is AB4E type, which means 4 bond pairs and 1 lone pair. 4 bond pair and 1 lone pair, right? So if we are considering this molecule, we will experience that here you can see that there will be the structure or the geometry of trigonal bipyramidal. So if you are considering here, this will be our A molecule. Right, this will be the structure. If you am considering these bond pairs only, it will look like a seesaw, right? Seesaw, right? If you are considering the lone pairs, if you are not considering the lone pairs, it will be bond pairs, right? If you are considering the bond pairs only, it will have a shape of seesaw shape. So we will call this particular molecule has a shape of seesaw, right? For example, SF4. Clear? The next type it is AB3E2 type, which means that 3 bond pairs are present along with 2 lone pairs, right? 3 bond pair with 2 lone pair. So if you am considering the AB3E2 molecule, its structure will be we feel that it must again have a trigonal bipyramidal structure, but again we are considering only bond pair of electrons. So if we are considering the bond pair of electrons, it will looks like a T shape, right? It will looks like a alphabetic T alphabet. So we will call this shape as a T shape. Clear? The main example is ClF3. You can draw this structure as this also, and also it again looks like T shape, so we will call this shape as a T shape. Clear? The next type it is AB5E type, which means that AB5 types, which means that it contains 5 bond pairs. 5 bond pairs and 1 lone pair, right? 5 bond pairs and 1 lone pair. Again, if we are containing 5 bond pairs and 1 lone pair, we will consider it as an octahedral shape, right? All the 6 atoms are arranged like this, octahedral. But in actual practice, whenever we are considering the bond pairs only, the shape will become square pyramidal. The shape will become square pyramidal. We are just ignoring the lone pairs, then it will become square pyramidal. For example, BRFY. Clear? Now the last type of molecules with lone pairs is that AB4E2 type, which means 4 bond pair with 2 lone pair. 4 bond pair with 2 lone pair. Again, what will be the expected geometry? 4 bond pair plus 2 lone pair. Octahedral, right? Because the 2 lone pairs will be arranged in the opposite manner. As you can see here, these are the 2 lone pairs and these are the 4 bond pairs. This will be the octahedral structure. But in actual practice, again due to the lone pair repulsion, we will say that it will be arranged in a square planar manner, right? By just ignoring or hiding the lone pairs, we will just look into the structure. Then it will form like that. It is in a square planar structure. For example, if you are considering the XeF4 molecule, this is again XeF4. 2 lone pairs are existing in between on 2 F molecules, right? Just opposed to that. This will be the final structure of XeF4. Clear? This is the final summary of the molecules with a lone pair on central atom having the different shapes. As you can see here, this is the first type, right? AB2E type, which means 2 bond pairs plus 1 lone pair. 2 bond pairs plus 1 lone pair. Then, I think you have an idea about the hybridization. Otherwise, there will be a single trick, a single number to predict the hybridization, that is a steric number. Right, this will be the steric number, which means the number of sigma bond plus number of lone pair. If you are considering, this is the bond pairs, right, which means it is a sigma bond. So 2 plus 1 will be 3. 3 means if the number is getting 3, it will be sp2 hybridization, right? Then if it is 4, it will be sp3. If it is 5, it is sp3d. Then if it is 6, it will be sp3d2. Then for 2, it will be sp. Right? These are the trick or the number or the steric number to find the hybridization here. Here it is 2 plus 1, 3, right? 3 means it will be the sp2 hybridization. Here it is sp2 hybridization. The predicted shape or geometry was trigonal planar, but whenever we are considering the lone pair, it will become V shape or bend shape. Again, for AB3E type, it is 3 plus 1, 4. 4 means sp3, right? sp3 hybridization. For the sp3 hybridization, the predicted shape was tetrahedral, but in actual practice, whenever we are considering the lone pairs, it will become, the shape become pyramidal. Then what about the next one? AB2E2, which means 2 bond pairs plus 2 lone pairs, 2 plus 2, 4. Again, sp3 hybridization, the predicted shape was, predicted geometry was tetrahedral. Then while considering the lone pairs, it will become V shape. Then the fourth one, AB4E type, 4 bond pairs plus 1 lone pair. 4 plus 1, 5, right? 4 plus 1, 5. 5 means sp3d hybridization. The geometry was trigonal bipyramidal. But if you are considering the SF4 molecule, right? Due to the presence of that lone pairs, it will looks like a distorted tetrahedral or seesaw shape. Clear? Seesaw shape. Then what about the second? Next one, AB3E2, right? 3 bond pairs plus 2 lone pairs, total 3 plus 2, 5. 5 means sp3d hybridization, trigonal bipyramidal again, but actual shape was T shape. Examples are ClF3 and BrF3. Then the next one, AB2E3 type. This is a special case. You can just memorize these things. AB2E3 means 2 bond pairs plus 3 lone pairs. 2 plus 3, sp3 hybridization, trigonal bipyramidal, right? But for these special cases, you will experience that it is linear bipyramidal. Just to memorize only. Then these are the major important cases. That is the fifth one. AB5E, 5 plus 1, 6. 6 means sp3d2, octahedral geometry. But actually it is square pyramidal, right? BrF5 and IF5. Then 4, 2, right? AB4E2 means 4 bond pair plus 2 lone pair. 4 plus 2, 6, octahedral. But it will be square planar in the case of XCF4, BrF4 minus. Then the last one, AB6E type, which means 6 plus 1, right? If it is having 7, it will be having the hybridization of sp3d3, having the shape of a geometry of pentagonal bipyramidal. But actual practice, if you are considering the XeF6 molecule, it will have the shape of distorted octahedral. Clear? Okay, so far we have just discussed about the VSEPR theory. We have seen that more atoms are present, right? We will be discussing about the valential electron pair repulsion theory, in which we will consider the molecules with 0 lone pair as well as without 0 lone pairs, right? 0 lone pairs as well as lone pair with bond pair. So we have seen the different geometry and shape of the molecule. This will be very important. Along with examples, questions will ask in the JEE Main exam also. Now, here is some practice questions for you. The first question is, the octahedral molecule among the following is? Options are given here. First one, it is SO3, CHCl3, SF6 and PCl5. Find out the molecule having the octahedral geometry. What will be the answer? Option 3, right? SF6. This will be the structure of SF6 molecules, which mean that it will be in the sp3d2 hybridization, or you can calculate the steric number also. There is no lone pairs, right? Only bond pairs, or number of sigma bonds is equal to 1, 2, 3, 4, 5, 6, which means 6 is equal to sp3d2. sp3d2 because of there is no in lone pairs, so it will experience the same geometry as well as experienced by the hybridization. So geometry will be, or the molecule will be having the octahedral geometry. Clear? Here is the next question. In the structure of ClF3, the number of lone pairs of electrons on the central atom. We have seen about the ClF3 structure, right? This is a special case, have a different shape. You have to find out the number of lone pairs present on the central atom. Number of lone pairs present on the central atom. Just go through the shape of the molecule or the geometry of the molecule, so you can identify what is the shape of that molecule. ClF3, right? ClF3 having the 2 lone pairs and its shape is T shape. So, our question is we have to find out the number of lone pairs, right? Number of lone pairs in the central metal atom. The central atom is chlorine here. It is having 3 bond pairs plus 2 lone pairs, which means option 3 will be the correct answer. Clear? Here is the next question. The shape of water molecule and bond angle in water molecule according to the hybridization concept. Not about the VSEPR theory, it is asking about the hybridization concept. What we are accepting from the shape of water molecule. In the case of water molecule, 2 lone pairs are present, right? 2 lone pairs are present in the case of water molecule. So, if you are considering only the hybridization, what will be the steric number here? Steric number the total number of sigma bonds, that is 1, 2, right? Plus number of lone pairs, again 2 lone pairs. So, I am taking here 2 plus 2, that is equal to 4. If the number is 4, we will call it as sp3 hybridization, right? sp3 hybridization means tetrahedral geometry is present here, having a general angle of 109 degree 28 minute. Clear? According to the hybridization concept, tetrahedral and 109 degree 28 minute will be the bond angle as well as shape of the water molecule. But we are considering the VSEPR theory, the shape will be bent. Clear? The next question is the shape of AB3 E-type molecule. AB3 E-type molecule. What is the answer? AB3 means 3 bond pair plus 1 lone pair. So, what will be the shape? Pyramidal, right? The question is about the shape, not about the geometry. If you are asking about the geometry, geometry will be tetrahedral as expected from the hybridization, but shape will be pyramidal. You can take the example of ammonia molecule. It must have 1 lone pair as well as 3 bond pairs. Clear? Here is the next question. which of the following has square pyramidal geometry? Sorry, square pyramidal structure. Which of the following has square pyramidal structure? First, you must have an idea about the complete table as well as structure, shape, geometry and the hybridization of the particle molecule with a lone pair and without lone pair. So, you must be able to answer this question. Square pyramidal structure. BRFI, right? Option 1 BRFI having the BRFI, right? Here. BRFI is belong to AB5 retype, which means 5 bond pairs and 1 lone pair. So you can see here, expected shape was octahedral, but in practice it will become square pyramidal, just like IF5 also. Clear? Yes, option 1 will be the correct answer. Okay, that's all about from my side for today. We have successfully discussed about the VSEPR theory, which means that it predicts the shape of the molecules, right? According to the valence shell electron pair repulsion, there will be 2 types of electron pairs, bond pair as well as lone pair. Whenever we are considering the lone pair also, the geometry of the molecule changes, right? Shape will arises there. That is the basis of VSEPR theory. So, again the gentle reminder about the AITS. All India test series for the JEE session 2 and JEE advanced. You will get a discount of 2,999 by using the YouTube 50 off code. So don't miss it. Just enroll now. Okay, that's all from my side for today. Tomorrow on the next session, I will be coming with the valence bond theory, which is again more important theory as according to the chemical bonding and molecular structure. So till then, bye bye all of you. Take care. Thank you so much. And don't forget to subscribe our channel also. Like and share the particular session also. Thank you.